Hi, this video demonstration is designed to get you started on making perturbation analysis or performing perturbation analysis on the sustained vowel. We either refer to as jitter and shimmer, but we also generate measures of signal to noise ratio, and all of these are measures that have some correlation with vocal quality. This is a sample that I've collected of myself actually producing about a 3 to 5 second prolonged ah. I'm going to play this for you so you can hear it. And our goal here is to limit our analysis to the middle 1 second of the production. So if you recall how to basically do basic measures with the left and right cursor, if you look at, we place our left and right cursors around the duration of the prolonged vowel, we see that it's around 4.5, or if we look up here, 4,677 milliseconds, so about 4.6 seconds. And what we basically do is we're going to try and shoot for a spot right in about the middle second. The only exceptions would be if there's something really unusual going on there that is not typical of the vowel. So what I do basically is I bring in my cursors from left and right until I find a duration here in the middle that's about 1 second, and you can see up here this is 999 milliseconds. That's pretty close. And I'm going to be doing my analysis on that. What I'm going to do is expand that. So now you're actually seeing the individual oscillations. And we're going to use make a number of measurements here, but fortunately the measurement tools are done automatically with just really a button click of the TF32 tool. We go up to the view. This is commonly, if you're looking to do an actual analysis or a display, you go to View, Open, and you go all the way down to this selection called Jitter. You click on that, and you should get a window that looks something like this. And it's all you have to do is click the Compute button, hit Compute, and it goes into that section that we selected and performs a number of analyses. The first analysis is that it does a fundamental frequency analysis where it measures each pitch period, and we see that that is 106 Hertz right here. We want to record that. We'll put that in our report. And then we next want to get an estimate of what we refer to as jitter. And jitter is just the cycle-to-cycle variations in the fundamental frequency as you move from cycle to cycle. And we don't produce, our vocal folds don't vibrate exactly the same rate every single cycle. And this jitter provides an estimate of how much variation there is in the fundamental frequency. And we don't want to use this measure here just called JIT. We go to the percent JIT, which is a percentage of the fundamental frequency, and it's 0.32. Typically values below 1% are considered normal, and this is a normal voice. Then we also are going to record the percent SHM, that's percent shimmer. And shimmer is a measure of the cycle-to-cycle variation in amplitude. So how what the peak amplitude of each cycle of the waveform and how it varies over the duration of the measurement period, which is what that middle 1,000 milliseconds. When we were going to record that to be 1.38, we don't have good norms on this, so this is a little more difficult to interpret. And then finally there's this measure called SNR, and that is the signal to noise ratio, or the harmonics to noise ratio, and that measures the degree of periodicity of the signal, how much relative to the amount of noise. So signals with very high signal to noise ratios means you have a lot of tone associated with the vibration of the vocal folds and less aperiodic noise. Noisy voices have very low signal-to-noise ratios. Typically values above 15 or so are considered normal, but it really depends upon the manner in which the measure is calculated. You can record that. Once you do that, you're all finished. You have all of the key numbers that you need to then include in your acoustic analysis results of your report.